So, dear colleagues, today is the day of our seminar, and this is the last seminar before Christmas and New Year's vacations. And today we have a lecture from Czech Republic, Professor Radek Cibulka. He's graduated from University of Chemistry and Technology, Prague in 1996. In the same university, he obtained PhD in 2002 and habilitation in 2009. He had his postdoc in Department of Organic Chemistry of University of Regensburg in Germany with Professor Koenig in 2003. And then after this, he started independent scientific career, firstly as assistant professor, then as associate professor, and now since 2017, he is a full professor in organic chemistry at University of Chemistry and Technology, Prague. His main research interests are heterocyclic chemistry with application of photocatalysis, organocatalysis in the redox reactions, Flavin-based redox and photoactive systems, as well as biomimetics reactions. Professor Cibulka was awarded by numerous awards, including Prize of Joseph Hlavka, Young Chemistry Award in Organic Chemistry from Sigma Aldrich, Alfred Bader Prize for Organic Chemistry, Chemistry Europe Fellow, and Rudolf Lukáš Prize from the Czech Chemical Society for excellent results in the field of organic chemistry. Therefore, it's a pleasure for us to listen to your lecture here, okay, and you can start it.
Valentin, thank you very much for very kind introduction. My regards from Prague to Kharkiv. And ladies and gentlemen, I will start with this photo, which is on the first slide here. And this is a photo I did during my visit on 2018. And I really believe, and I'm sure that I can do the similar photo very soon, and I will visit Kharkiv again in peacetime. So I would like to start with the area which I'm focusing with my colleagues in the lab, and it is using light to mediate chemical reactions. And light is something which can help us a lot doing reactions which are usually not possible in dark. And for this, we are using a special type of compounds which are called flavins and deazaflavin-based. And today I will a little bit more focus on the area of reductions. In principle, light can be considered as a chemical reagent, and it can help to jump the energetic barrier when absorbing the light by any component of the reaction, and then we can do either exergonic reactions with high energetic barrier, or what is even much more challenging is that we can even jump the energetic barrier in the case of endergonic reactions. And in such a case, we in principle store the energy into chemical bonds. And of course, nature do it for very well, because we know one of the most famous reactions, which is photosynthesis, where we, by using light and the special system, we can drive the chemical reactions of CO2 with water to produce CC bonds in glucose. And on this way, we are able to store energy about 3000 kilojoules per mole. And it is really very high energy. In chemistry, we can use similarly the energy of light and to pump it into the system and store it into chemical bonds. And in principle, we are calling such type of reactions photochemistry. And when we are using any compound which is present in catalytic amount in the system, and it is the only the only compound which is able to absorb the light, then we are calling it photoredox catalysis. And this is the area which was developed within last 20 years. And today it is one of the alternative which we can use for our organic synthesis. And how it works, we are using any dye which absorb the light, and this dye is excited by the light. Usually we can use different type of light. We can use UV as well as visible light, but I will explain it you later that the visible light is advantageous. After absorption of light, we are producing a compound which is in excited state. And the most important principle is that in excited state, any molecule is much more reactive in comparison to ground state. It means that it became stronger reducing or oxidizing agent. And by this way, it is able to oxidize or reduce. This example is for oxidation. So it means oxidize any substrate which forms then a radical or radical cation. And this radical cation then reacts with other species to produce our product. Of course, to be catalytic, then the catalyst should be regenerated in the catalytic cycle by any sacrificial reagent, or also we can have the catalytic cycles where we can really use this product to regenerate the catalyst. In principle, as I already mentioned, we can use the whole spectrum for the photoredox catalysis, but you can imagine that going to UV light, we can have photons with very, very high energy. It is nice from the point of view of excitation. On the other hand, we have the problem because the energy, for example, of the light, which is in UVA area, it is the energy which is enough to cleave the carbon-halogen bond. And this is, for example, the reason why you cannot store brominated compounds under sunlight, because in such a case, the bromine containing compounds are not stable, and you can see formation of bromine within 1 month area if you have on the bench your brominating compound. And this is the problem, because using the very strong UV light, it is not selective. You can break the bonds you don't want to break. And this is the reason why photoredox catalysis today much more prefer to use visible light from 400 to higher wavelengths. Why? Because then we can selectively excite our photocatalyst without problem with excitation of other regions, and we can selectively provide our catalytic cycle. It has also some practical reasons why it is advantageous, because we can that are practical aspects, because you can buy LEDs, which are not so expensive, and we can also work in normal glass. So it is not necessary to use silica glass apparatus, which are very expensive. So we normally are working using LEDs, and in normal Erlenmeyer flask or in Schlenk tube. It depends which type of reaction we are doing. I already mentioned that using light, we are producing very strong oxidizing or reducing agent. It is shown here. For example, if we can have oxidation of compound B with the compound A, it means that we should transform this electron to compound A, so it means to this orbital. But it is impossible in ground state if it is on this, if the levels of HOMO-LUMO levels are of this energy, because it's uphill and it is not possible. But after excitation of A, I said, it could be photocatalyst, for example, we have free space here, and after that we can have very fast transform of an electron to this area, and we have formation of the radical anion, which is the case of catalyst, and compound B is oxidized. This is the principle of using light for formation of strong oxidizing species. And the reaction is can be described by the Gibbs energy, of course, and it should be negative. And in principle, the most important value is here is energy of reduction or reduction potential in excited state of our photocatalyst, which can be easily found by measuring cyclic voltammetry. So it means the reduction potential on ground state and energy of excitation, which can be found in absorption on and fluorescent spectra, for example. And what we need, of course, that our oxidizing agent has this excited state redox potential higher than our substrate. And the same works for reduction. So I will go much quickly. So if we reduce C with A, we can have this situation. But after excitation, we now have the possibility that the electron can go to the C, and C is then reduced by A in excited state. And in the case of reductions, we, of course, need that our excited state potential of our catalyst is much negative in comparison with our compound. So in principle, we can use different types of dyes for our photocatalysis. And many of them are commercially available. You can see the ruthenium, iridium compounds, which are pretty much stable and also very strong reducing or oxidizing agent, depending on substitution. We can have acridinium salt, we can have eosine, which was one of the first photocatalysts used in photoredox catalysis. And originally it was used for photoimaging. And this catalyst, which was used which is used for reductions, and it was really found specially for reductive photoredox catalysis. But if you can see here, these catalysts are not so cheap, with the exception of eosine, which is produced in high amount. And this is also one reason why the chemists are looking for new and new photocatalysts, which especially among organic molecules can be much more cheaper in comparison, for example, with these complexes. And of course, the other motivation, and maybe the most important motivation, is to have much stronger reducing or much stronger oxidizing agents. And in our laboratory, we are focusing on the catalysts which are derived from vitamin B2, from riboflavin, which is known to be cofactor which is responsible for electron reductions, either 1 electron or 2 electron reductive processes in many different flavoenzymes. We have in principle more than 1,000 flavoenzymes in organisms. And you can see that the flavin can form either radical anion or the anion species. And of course, in oxidized form, it can work as a reducing, or in reduced form, it can work as a reducing agent. So there is oxidant and there is reductant. And moreover, the flavins are very nice species which are yellow. This is also the name flavin, which comes from flavus, yellow. And this is this yellow-orange color, which comes from absorption. And you can see this also slightly greenish compound because of fluorescence. And the fluorescence appearing here looks or shows us that flavins probably can be also used in photoredox catalysis. And this is what we are doing. We are playing with the structure of flavin. For example, we can replace this nitrogen to carbon to have deazaflavin. We can change the configuration here of these double bonds to have alloxazine as a other derivative, or we can introduce here even ethyl ring to have quaternary. It means positively charged flavins, which are also very good oxidizing agents. And in principle, we are looking for new flavin derivatives and, of course, for their new applications in photoredox catalysis. I will talk today mainly about reductions, but I will start with oxidative chemistry. And the reason is that the flavins were from the beginning considered as a very strong oxidizing agent in an excited state. But when we consider the flavin as an oxidizing agent, you can see here redox potential, which is really much lower than, for example, substrate, which can be called as a benzyl alcohol. And oxidation of benzyl alcohols, this is something, one of the oldest application of flavins in photoredox catalysis. But you can see if you count this Gibbs energy, it is really very, very positive. So it means that the flavin in ground state is not able to oxidize this paramethoxybenzyl alcohol. But after excitation, we have the species which has much more positive redox potential, much higher than this paramethoxybenzyl alcohol. And this species can really oxidize this to form radical cation, which can further react to aldehyde. So we can use really the flavin as an oxidizing agent, which is able to oxidize benzyl alcohol to aldehyde. In this reaction, flavin is reduced to reduced form, and this form is reoxidized by oxygen. So in principle, we can use flavin in catalytic amount, and it is catalyst of oxidation of this benzyl alcohol by oxygen to form hydrogen peroxide and our aldehyde as the only products. But you can see that this oxidant is not so strong to oxidize, for example, these species, but it was shown before by Fukuzumi or by Robert Wolf that you can introduce here the scandium species, which is even much stronger oxidizing agent, and you can oxidize this, and also this. In our approach, we wanted to work without any metal, and this was the reason why we not introduced the metal to have the flavin as a ligand, but we tried to introduce positive charge here. Even in ground state, we have now very strong or relatively strong oxidizing agent, but not still so strong to oxidize these species. But after excitation with violet or blue light, we have extremely strong oxidizing agent, which is really able to oxidize everything. And these applications can be shown here. For example, using 5 molar% of this catalyst, 450 nanometer slide, acetonitrile as a solvent, and a little bit more elevated temperature, we can oxidize benzyl alcohol to corresponding acid, or even methyl group to corresponding acid, or methylene group to corresponding ketone. And you can see here that each reaction works very well, with the exception of of oxidation of compounds having here very negative electron withdrawing group. And for this reason, we need a little bit improve the conditions to have carboxylic acid in the system. So I introduced flavins as a very strong oxidizing species. But now I will speak about reductive chemistry. And it was maybe 10 years ago when we were talking about flavins as a photocatalyst, also with Burkhard Koenig. And both we had opinion that flavins probably will be much more suitable for reductions than for oxidations. And we have also one parallel in the nature where the flavins are working as a strong reducing agent, and this is shown here. Flavins are known that they are working in photolysis as compounds responsible to cleave this cyclobutane skeleton back to thymine or uracil moieties. The problem is that the thymine and uracil in our DNA, after irradiation with UV light, forms these cyclobutanes, and such DNA is not functional anymore. But for example, flavors have the enzyme which is called photolysis, and in this enzyme, the flavin is responsible for back cleavage and restoration of function of these enzymes. And the principle is here. The principle can be described that the flavin is reduced. We have reduced flavin, which is irradiated, and in excited state, it's a very strong reducing agent, producing this radical, and then there is a cascade of reactions going to free uracil or free thymine. And the mechanism of this was very investigated by Sankar, which was awarded by Nobel Prize few years ago by this founding. And I will go back to this slide when I would like to explain why the reductive catalysis and for which reactions are the reductive catalysis important. And of course, we have plenty reductions in organic chemistry, and many of them are done also by a very strong reducing agent like alkaline metals and so on, so on. And one of aims of chemists is to generate phenyl radical going from any aromatic species by one electron reduction. And this is very helpful because if we have phenyl radical, it can react with different type of species, for example, with double bond, with heterocycles, and with other compounds to produce novel CC bond. CC bond here to heterocycle, C-boron bond if we are reacting with boronic compounds, or even we can reduce this aromatic species to form the free benzene ring. And this can be helpful when we control such type of reactions. But the problem is that these compounds are sometimes of a very negative reduction potential. You can compare it. Of course, you probably know very nice applications of diazonium salts. Diazonium salts are known to produce some radicals and some types of reactions which are in principle responsible, for example, for production of chlorobenzene. But producing diazonium salt, or you can see iodonium salt, or these compounds are not so easy, and in principle commercially available compounds are much more from the area of halogen benzenes or halogen containing aromatic compounds. And the problem is, if you see that really reduction potentials of such compounds are very, very, very negative, and it's very difficult to reduce them. And we have in principle several possibilities how to do that. When reductive photocatalysis started, we used single photon photoreductions. What it means that the photocatalyst is excited, in excited state is able to reduce the this halogen benzene to form this radical anion, and the photocatalyst is then regenerated by any sacrificial reagent. Such a radical anion is then very easily producing halide and corresponding radical. But you can see that this reaction ends here, somewhere about -2.2 volts, and we have no stronger photocatalyst even after excitation. The second principle found by Burckhardt-Koenig is based on consecutive photoelectron transfer photoreductions. So it means that we use two photons. The first one is to produce the radical anion, and this radical anion is excited again to form excited radical anion. And these particles are very, very strong reducing agent, and we can compare reduction power with sodium and even with lithium. Sometimes we can replace this part also by electrochemistry, and we have in literature some applications of combination of electrochemistry and photochemistry. And when I can tell something about the very strong reducing agent, so it is one radical which is formed from this acridinium salt, and very recently published this benzo or indole thiol forming this anion which is extremely strong after excitation. So what about flavins? We started to think about using riboflavin tetraacetate and its derivatives, but we thought about that maybe it would be much better to go towards chemistry of deazaflavins. You can compare the deazaflavins had much more negative reduction potentials. So in principle, they can be much more suitable for reductions in comparison with this flavin. And we started with this, and studying the reductive properties of this compound, we found that it easily forms this radical or a radical anion, depending on the amount of protons in the system or this reduced agents. But especially this radical was surprisingly relatively stable when phenyl ring was here. You can see this is oxidized form. Then it forms this radical, which also absorbs visible light around 400 nanometers. It can be seen here when we apply potential about -1.4 volts. So it means this reduction potential. That is the formation of this radical. And this radical was found that it is really very strong reducing agent with potential about -3.3. And we apply this catalyst for reduction of such difficult substrate like methoxy, bromobenzene, so bromoanisole, which can be reduced by this catalyst. And we found that when we have this original catalyst, so it means this with phenyl ring, we can have very nice production of the reduced species, which seems that we are able to reduce this compound. With phenyl ring, it is much better than with isopropyl, and much better when this hydrogen is here. The reason is the stability of the radical being here. And the mechanism found was that the flavin is excited, then it takes an electron from the sacrificial reducing agent. This is an amine, for example, dipair. And this amine reacts, or this amine put the electron here to form the radical anion. Flavin radical anion is excited again, and the excited species is such strong as I described before, being able to reduce this aryl halides. And this was very exciting finding that such flavins are very strong. But we found one problem in the system, and it was that this flavin radical, in the presence of dipair, which was formed, this radical cations, forms such a radical pairs. Of course, this is negatively charged, this is positively charged, and this pair in excited states can very easily undergo back electron transfer from flavin back to amine, and we are forming here this starting catalyst, and it decreases the yield of our photocatalytic system. And it was the reason why we started to look why it is the true, and we found that the problem is that this catalyst has a relatively low inter-system crossing. So it means transformation from singlet to triplet excited state. And with the aim to increase this inter-system crossing yield, we introduce heavy atom, which is known to support this inter-system crossing usually. And you can see it was very successful having these two catalysts. The problem of this one was that the bromine was directly on this phenyl ring, and it means that after excitation we lose the bromine atom from the system, and it was not so active anymore. So that was the reason why we have chosen this catalyst as the best one, and you can see that we really were able to reduce very difficult substrates. For example, chloroanisole, also the compound with 2 methoxy groups, also compound with 3 methoxy groups, or these derivatives with relatively good yields. And it works also preparatively. You can do it in relatively high amounts. So it was a story about dehalogenation, which is reaction which used usually as a model reaction to show reductive properties of the system. And we also tried to find application of our system. One application we found between Deprotection of compounds, which was studied by Tanya and also by Eva. And this tosyl group is usually used as a good protecting group to amines. And today, also the authors are using this good sulfonyl group containing trifluoromethyl group, or even perfluoroalkyl groups in general. These protecting groups are very helpful. It helps us also in the synthesis because this very strongly electron withdrawing groups, for example, allow introduction of any alkyl group to this position, and it is very easy to work with such derivatives. But the general problem is how to remove the protecting group, and it is usually done under very harsh conditions, by reductive conditions or harsh conditions by acid-base hydrolysis, and it is the problem for the rest of the molecule. Even worse situation is here with trifluoromethyl or trifluoroalkyl sulfonyl groups, which are really much more difficult to remove than this tosyl group. There are some novel ways how to deprotect it. For example, using this acridinium salt, which I already showed you as a strong reducing agent, but it was tested only for tosyl derivatives, or using this very electron-rich compounds, and to use it for deprotection of this trifluoryl group, of this trifluoromethyl containing group. But still there is any general group or general method which can be used for all such sulfonyl compounds. And for that, we try to use our flavin derivatives. This is which you already know, but we thought about that maybe we can go from this deazaflavin to deazaloxazine, which is even much more stronger reducing agent even in ground state. And we really found that this compound is extremely strong reducing agent, helpful in this chemistry. You can see we have 8% of the catalyst, 400 nanometers, basic conditions, and DPA, which is used as a source of electrons. And you can really cleave the nitrogen-sulfur bond. It means deprotect amine in the case of anilines, in the case of anilines with different groups, in the case of secondary or tertiary anilines, also in the case of phenols. And what is really challenging, that we can do that also with triphenyl groups or even nonaphenyl groups, which means that it is this perfluorobutyl group. And the mechanism is similar as for dehalogenations. So it means that the catalyst in excited state in the form of radical anion, which is formed using the sacrificial donor, is responsible for 1 electron reduction of this very difficult, which is the species which is very difficult to reduce. And this radical anion then produces the amine. What is important that the other product is this sulfinate. It means the salt of sulfinic acid. And I will show you in the next slide that it is very important species, because what we have found that we can even to set the conditions that we can do triple derivative removal, or we can even to remove the alkyl group from this system. So then from this protected secondary amine, we are producing primarily anilines. And how it works, I already showed you this catalytic cycle, that we are producing the amine and this alkyl sulfinate. But in the case when we have this trifle, so we were talking about this very important species, which is this alkyl sulfinate, and this alkyl sulfinate then can be oxidized by the flavin again to form this radical, and this radical take an electron here to form this radical, and finally we can have this imino species, which is then hydrated and to form the final product. I talk about that we can form this aniline, and it is the product of the reaction. So the catalytic cycle is, dirty nigger. I think that there is then finishing this our catalytic cycle, and the SO2 is something which is used to reoxidize this radical to restore our catalyst. I showed you that the flavin can be very strong oxidizing agent and very strong reducing agent. And what about to put it together and to utilize both of them for any practical application? And we thought about one practical application, and it is chemoselective oxidation. This is chemoselective oxidation because we know that some chemistry is not so easy, even if we have many different oxidizing agents. So it means that oxidizing alcohol to aldehyde or acid, yeah, it looks nicely, but you should have very chemoselective systems. We have some of them. We have also chemoselective system for the most difficult task is to have two different oxidizable species in the system. So it means to oxidize, for example, only alcohol and not to oxidize sulfide. And the same here, for example, to oxidize only alcohol and not to oxidize the methylene group. And one possibility is to use photoredox catalysis. But the problem of oxidizing photoredox catalysis is that you need to have sacrificial oxidant. And sacrificial oxidant in photoredox catalysis is usually oxygen or any even stronger oxidizing agent, which are producing very reactive species like singlet oxygen, hydrogen peroxide, or superoxide. And these are responsible for many different undesired oxidations. So we thought about not to use sacrificial oxidant in the system. And one possible solving the problem is known in the literature, and it is to use any catalyst, usually as, for example, cobalt complexes, which are able to be reoxidized with proton to form the hydrogen. So it means hydrogen-coupled oxidizing reactions. But we thought about another way to use solvent for reoxidations. And we found this system by the way that we tried to construct catalysts which will be either both strong oxidizing and strong reducing agent. I showed you some couple of minutes ago that this flavinium salt can be a very strong oxidizing agent with this potential. I also showed you that flavins or deazaflavins can be very strong reducing agent doing this chemistry. So we prepared or thought about such a hybrid, which is deaza and also flavinium salt. And we tried to test them in both oxidations and reductions. And we found very interesting properties of this catalyst. We studied this oxidation, so it means the secondary alcohol goes to the ketone, and this in the presence of this new catalyst, which has carbon here and quaternary centrum here, working under oxygen, allowed us to prepare this ketone under with quantitative yield. This is what we expected, but unexpected result was found when we did the reaction under argon. It means that we have no oxygen in there, and question was, what is sacrificial oxidizing agent here? Very probably acetonitrile, which was used here as a solvent. We tested other solvents like acetone, which has very little oxidizing properties. Dimethyl sulfoxide, a little bit more oxidizing properties. And you see that the results were not so nice as in the case of acetonitrile. And this was the reason when we started to use acetonitrile as oxidizing, or it means to use a solvent as sacrificial oxidizing agent. And we studied the mechanism if it is true, because to reduce acetonitrile is really not so easy because it has very low, very negative reduction potential. So this is the flavinium salt with nice spectrum, absorption around 400. It is excited. Then we studied if this compound is able to oxidize our substrate. It's true. We use fluorescent quenching experiment to show that this species in excited state is able to oxidize this alcohol. So it was the first step. The second step, we identified this radical by EPR, very nice measurement with experimental calculated spectrum, which were the same. And also we try to generate this radical using sacrificial reducing agent. You can see that it was formed here. And the same result we obtained by electrochemistry. So it means really we have this radical which can be excited by 400. You can see that it absorbed here. And in excited state, it can work as a strong reducing agent. Probably it is able to reduce acetonitrile to form this solvated electron, which is in equilibrium with the dimer radical anion. This is known that these species can be monitored by UV or maybe better said IR spectroscopy. And you can see it here that this electron, which is solvated in acetonitrile, is visible here, and it corresponds pretty nicely with the data. These are these dots from the literature. So we found that really we are producing solvated electron, which is then forming this radical anion, and after hydrolysis, there is production of acetaldehyde, which we found and also detected using hydrazine. So we found completely new procedure, which is very chemoselective and which uses acetonitrile as the only sacrificial oxidant. So it means we need only catalyst, light, and solvent, not oxygen. When we compared experiment under oxygen and under argon, you can see here nice chemoselectivity, because under oxygen, we are oxidizing both alcohol and sulfur. But under argon, there is only the dihydrogenation reaction and not this oxidation, because we have no oxygen in the system. So under argon, we have pretty nice chemoselectivity. Very similarly, under oxygen, we can observe both oxidation of alcohol and the methylene group to ketone. But under argon, we have only oxidation of alcohol to the ketone. And the same here, we can see nice selectivity, because under argon, we can have only oxidation to aldehyde and not to carboxylic acid, which is known to be observed under oxygen. So you can see this very nice application of flavins, and we can tell and we can conclude that really flavins can be very strong oxidizing agent and also very strong reducing agent. And we found many interesting synthetic applications of such reductive species in organic chemistry. We also found that we can have the species which is really both oxidizing and reducing. And for the future, we are thinking not only to combine photocatalysis in oxidative and reductive chemistry, but also we can use flavins as organocatalysts and biocatalysts, of course, because you can use also enzymes directly as a strong oxidizing and strong reducing agents. At the end of my talk, I would like to thank all people for very hard work, especially when we are talking about reductive chemistry. It's Tanya and Eva, and when we are talking about the chemistry oxidation, combination of oxidations and reductions, it is Robert. Everything is covered by Eva, and also with other people are involved in our very nice work about flavin catalysis. I would like to thank also our collaborations, both in Czech Republic as well as in abroad. I would like to thank all grant agencies for financial support. And finally, I would like to thank you for great attention, and thank you very much again for invitation.
Thank you very much, Professor Cibulka, for your lecture, and sorry for this accident during your lecture. It was hacked by Russia Federation to prevent even scientific events in Ukraine. Unfortunately, we have only 10 participants now.
Yeah, we lost some of them. Yeah, but
yes.
you know, it looks that it shows that the situation is not normal. Yeah, that's unfortunately. Yeah.
But maybe somebody from our participants have questions to our lecturer concerning this chemistry. And Yeah, okay. I have maybe some questions to you. First of all, it's about real application, preparative application, and maybe semi-industrial or even industrial applications of such interesting processes. What do you can to say about this?
In principle, it is possible, but we expect a relatively long way to go there, because for we can tell about industrial application, you need that your catalyst will be very, very, very stable. So it means that you can use it for many times. And this is a relatively problem with flavins and generally with all organic photocatalysts, because they are relatively non-stable. On the other hand, we can tell you that some of our derivatives are much more stable than the derivatives at the beginning of our work with flavins. So it means that, for example, for some small, not industrial, but maybe some relatively small amount application, like working with tens or hundreds of grams, I can imagine. So it means, for example, in pharmaceutical industry, in synthesis of APIs or something like that, I can imagine that such an application can be found.
Yeah, okay. And exactly about pharmaceutical. In some cases, you showed us yields of your compounds only NMR or HPLC yield. What about real yield and purity of your compounds after these procedures?
Okay. Yeah, I showed it not to be so long with explanations, but in general, especially for example, for these deprotection reactions, we know that we can isolate our products in very high purity, in good to some cases excellent yields. And the same is also for our chemoselective oxidations. So, of course, for comparison, we are using usually NMR yields, but in all cases, we also did the preparative experiments showing that it is possible to use these applications.
Okay, and purity of your compounds is rather high.
Yeah.
Okay. So, and my last question is, do you have other types of organic photocatalysis with such high potential for reduction as flavins?
As I showed you before, there is this acridinium salt.
Yes, I remember.
Which is really very strong. And when I start as an organic synthetic chemist to do something with reductive chemistry, so I will try this acridinium salt, then our flavin, and then one of these cyanobenzene derivatives. These are very strong and already well investigated.
Mm-hmm. Okay, thank you. So, dear colleagues, maybe somebody has question as well. Nobody. Okay, thank you very much again for your time, for your lecture, and have a nice evening today.
Thank you very much, and especially I wish you very noisy and good evening and all Christmas time in Kharkiv.
So, thank you. Thank you. So goodbye.
Valentin, bye.
I hope we will see.
Yeah.
Yes.
Me too.